Okay, this is lessons 9, 8, and 9, 9, quadratic, cubic, and exponential functions. So in lesson 9, 7, we discussed the difference between linear functions and nonlinear functions. Quadratic, cubic, and exponential functions are some of the most common types of nonlinear functions. So those are the three that we'll be looking at in these two lessons. Our main focus will be on graphing these types of functions. Though quadratic functions do have a couple of applications that we'll look at as well, but the main focus for these two sections will be on graphing. So as we go through these three just kind of general bits of information about the types of functions, you want to pay special attention to what the graphs look like. So for quadratic functions, these are functions that can be described by an equation of the form y equals ax squared plus bx plus c, where a is not equal to 0. Notice quadratic, those are the ones that have an x squared as the biggest exponent for x. The graph of a quadratic equation takes the form shown to the right, which is called a parabola. It's this U-shaped curve. So that U shape is a parabola. That's what the graph of a quadratic function looks like. Cubic functions. Functions that can be described by an equation of the form y equals ax cubed plus bx squared plus cx plus d, where a is not equal to 0, are called cubic functions. So the largest exponent for x in a cubic function is an x to the third. The graph of a cubic equation takes the form shown to the right. So it has this sort of a curving shape. Notice that in this case, it increases throughout the whole graph. It could also go the other direction and decrease through the whole thing. But it does sort of change direction in the middle somewhere. So there's on both the quadratic and the cubic, and you'll see the same thing on the exponential. There's no straight lines involved anywhere. It's all curves. So when we graph these, we're going to have to make sure that we graph them with curved lines instead of straight lines. And then the last one, exponential functions. These are a little bit different from quadratic and cubic. In linear, quadratic, and cubic functions, the variable is the base. So like in cubic functions, we had x to the third. In quadratic functions, we had x squared. In linear functions, we have x, which is just x to the first. The variable is the base for those. Exponential functions are functions in which the variable is the exponent rather than the base. An exponential function is a function that can be described by an equation of the form y equals a to the x plus c. And you see the variable x there is in the exponent, not the base itself. So that's an exponential function, where a is not 0 and not 1. The graph of an exponential function takes the form shown to the right. So it just makes this curved sort of shape. The bottom part of the curve will be straight across, or very, very close to straight across, actually. It's never exactly horizontal, but it'll very closely approximate it. And then it takes a sharp turn up, and it could fall and go this direction as well, either one, depending on the exact numbers for A and C, but it will have kind of this general shape. Okay, so let's see how we can graph these. Just as with linear functions, you can graph quadratic, cubic, and exponential functions by making a table of values. And that's what we will do. Now here's the difference between linear functions versus these three types of functions. In linear functions, you only needed 2 points, maybe 3, to make the correct graph, because you knew every single time it was going to be a straight line. And as long as you had at least 2 points, you could draw a straight line. Well, for quadratic, cubic, and exponential functions, because the graph is not a straight line and not even really a set shape, it's not good enough to just have 2 or 3 points. So we want to have as many as possible. And for these, we're actually going to come up with some specific points, but you want to have around 5 points total, and you'll see why in a few minutes. The nice thing, though, is that you're going to be able to use your calculator just to verify that your graph is correct. Now, that doesn't replace what we're going to do here with creating a table of values, but that is a good way to check it. Okay, so graph each function. And the first one we're going to start out with is y equals negative x squared plus 2. And this is a quadratic function because the largest exponent for x is a squared. So that's a quadratic function. So we'll make a table of values. And I'm going to leave space in the middle for us to work out the value of y, because these are a little more complex than the other equations we've had so far. And some good numbers to use for x most of the time, not all the time, but most of the time for these three types of functions are -2, -1, 0, 1, and 2. Okay. So then we'll plug in our values for x and we'll see what we get for y. So when x is -2, we have y equals, and we have the negative from the equation, and then in parentheses we have x is -2 squared plus 2. So when we evaluate this, we want to make sure that we do the exponent first. -2 squared is +4. And then this outside is treated like multiplication. That makes that 4 negative. So we have -4 plus 2, which is -2. When x is -1, it looks like this. We evaluate this first. That's -1 squared is 1. This makes it -1 plus 2 is +1. When x is 0, 0 squared is 0. The opposite of 0 is still 0. Plus 2 is 2. And then when x is 1, 1 squared is 1. That makes it -1. Plus 2 is +1. And then here 2 squared is 4. That makes it -4. Plus 2 is -2. Okay. So now we can go ahead and plot each of these points on our graph. So we have a point at -2, -2. We have a point at -1, 1. A point at 0, 2. At 1, 1. And at 2, -2. Okay. And if you remember back to the first page for what a quadratic function looks like, it makes this curved sort of shape. Now in this case our curve opens the other direction, it opens downward. But make sure that you're not connecting these with nice straight rigid segments. That's not the type of shape we have. What we have is a curved shape. So we want to kind of round each of these edges so that it looks like this. So rounded edges, not straight, solid segments. Want it rounded. So it looks like. Okay. Now I said that we were going to be able to use the calculator to verify this, and let me show you how that will work. On your calculator, if you go to y equals, this is where we can plot various equations and graph them and see what they look like. Now again, this is not going to replace what we've done here in this table of values. So it's just going to supplement it and allow us to at least check our answer. So if we want to graph y equals -x squared plus 2, notice when you go to the y equals button, each equation starts with y equals. So all we have to type in is -x squared plus 2. So there's negative, and then for x, we'll use this button to the right of the alpha button. It has an x in it among other variables. So x squared plus 2. And then just hit graph. And that looks like the same graph that we have. Now, if your screen is not showing this same graph, it may be that it's not zoomed in the same as this is. So when you hit zoom, the best place to go here usually is to zoom standard, number 6. So we'll arrow down to number 6, zoom standard, and then it should make your graph look just like mine if it didn't already. So that's a good trick to keep in mind. If the zoom doesn't seem, or if the screen doesn't seem to be zoomed correctly, go to zoom and zoom standard. Okay, and we can just verify here that this graph looks like the graph that we have, and that's what we wanted to see. Okay, let's try another one. For b, we have y equals 2x cubed, and because this is an x cubed, we know this is a cubic function. So we'll make a table of values again. And again, good values to choose for x normally would be -2, -1, 0, 1, and 2. So let's see what we get when we plug in these numbers for x. When x is -2, we have y equals 2, and then in parentheses, -2 to the third. Make sure that you're doing order of operations correctly and evaluating this exponent first before this multiplication. So -2 to the third is -8, times 2 is -16. So you can see here that this may not be the best point to use, because this is definitely not going to fit on this little graph here. Let's see what we get for the other values of x, though. When x is -1, we replace x with -1. -1 cubed is -1, times 2 is -2. Much better. This point will fit on the graph. We'll get there in a second. Let's replace x with 0. 0 cubed is 0, times 2 is still 0. Let's replace x with 1. 1 cubed is 1, times 2 is 2. And then we'll replace x with 2. 2 cubed is 8, times 2 is 16. So you see the pattern here, the symmetry at least. 0 and then 2 and -2, 16, -16. So we can see, if -2 doesn't work, +2 is not going to fit either. So when we graph these two are not going to fit on our graph, so we are actually not going to use these. Let's go ahead and plot these 3 points real quick. -1, -2, 0, 0, and 1, 2. And hey, look at that. That sure looks like it's going to be a straight line. However, we know that this is a cubic function. And we know from the first page that cubic functions look like this. So this is definitely not just a straight line. Well, what that tells us is that we actually need some other points somewhere, either up in this direction or down here, or maybe in between these two somewhere. So let's try something. It's not going to be a whole number, but let's try some other values for x so that we get a couple more points. And we'll use the calculator to make this a little bit easier as well. So let's try to get a couple points that are just on the outside of this part right here and this part right here, so that we can extend this a little bit further and kind of have a better idea of where the graph goes. So since we know that -1 and 1 gave us -2 and 2, we should be able to go just a little bit outside of here and get points that are also on the graph. So let's try -1.25 and +1.25. Okay, so when we replace x with -1.25, we have y equals 2 with -1.25 to the third. And here the calculator might come in handy as far as getting a number for this. We have 2, and then in parentheses, -1.25 to the third. It comes out to about -3.9 if we round that off. And here, it does not have to be exact, because you're not going to be able to get the exact point of this on the graph anyway. So we just want it to be close. And as you may suspect, 1.25 will probably give us +3.9. But let's do it anyway, just to make sure. So 2 times 1.25 to the third. And yes, we get 3.9 approximately. And that was, there we go. Okay, so let's go ahead and plot those additional points on the graph and see what our whole graph looks like. So at -1.25 and -3.9, there's -1.25 and -1, 2, 3, almost to 4 right there. And then 1.25 and 3.9. 1.25, 1, 2, 3, almost to 4. Okay, now you can see a little more of this curved shape here. If we wanted to, we could get another point, maybe around like 0.5 or something like that, and -0.5. But this should be enough to get a rough idea of what the graph looks like. So again, we'll connect these with a nice smooth curve. Again, keeping in mind what a cubic function looks like so that we know about what that curve should resemble. And then we'll use the calculator to check and make sure that that looks like the correct graph. So we go to y equals again, clear out the old equation that was in there before, and just put in 2x to the third. So 2x to the third. And then we'll hit graph. And hey look, this graph looks like our graph. That's what we wanted to see. Alright, let's do one more of these together. Again, we'll create a table of values. And we should be able to use -2, -1, 0, 1, and 2 again. Okay, when we plug in -2 for x, we have y equals 3 to the -2 minus 4. And now normally in section 9.4, yeah, 9.4, when we talked about negative exponents, we talked about changing this to a fraction. So this would be 1 over 3 squared. And that, that'd be 1/9, and then we can subtract 4, but our answer is going to be in a fraction form. Well, if I want to put that on the graph, I actually don't want it as a fraction, I want it as a decimal. So I'm going to use the calculator here just to make the math just a little bit easier, because really the focus right now is on graphing the correct graph. It's not really on whether or not you can do this correctly, though you should be able to anyway. But right now I just want to make sure that we can get the correct graph. So 3 to the -2 minus 4. And just a reminder, if you have one of the calculators that when you press this exponent button gives you the little exponent up in the top corner, make sure that after the -2 you hit the right arrow to get out of the exponent before you type -4. Otherwise it'll put -4 in the exponent with the -2, and that's not what you want. Okay. That comes out to -3.8 repeating. So if we round that off, it would be -3.89. And again, it doesn't have to be perfect. You're not going to be able to get it exact on the graph anyway. When x is -1, we have y equals 3 to the -1 minus 4. And again, you can put this in the graph also, or in the calculator also. It should come out to -3.6 repeating. So we'll round that to -3.67. When we put 0 in for x, we have y equals 3 to the 0 minus 4. And as we should know by now, anything to the 0 is 1. So this is 1 minus 4, which is -3. When we put in 1 for x, y equals 3 to the 1 minus 4. That's just 3 minus 4 is -1. And the last one, squared minus 4. This is 9. Minus 4 is 5. Okay. So let's put our points on the graph and see what the graph looks like. So we'll point at -2, -3.89. So -2, -1, 2, 3.89. And then -1, -3.67. There. 0, -3. 1, -1, and 2, 5. Okay. And if we remember back to the front page on what an exponential function looks like, this is basically the same type of graph that we got. So we'll just connect those again with a nice smooth curve. Here's where it's important to know what this graph looks like so that we don't just extend this, way down this direction or something. It really does appear to just flatten out here at -4. So make sure that you're drawing that pretty much horizontal. Okay. And of course we can graph this one on the calculator also to make sure that we get the correct graph. So y equals, clear out the old one, 3 to the x minus 4. When we graph, it should look like the graph that we have. Looks horizontal and then curves upward. Yep, that's what we have. Okay, so for the 3 try it yourself problems, you have a quadratic, a cubic, and an exponential, just like we did. For these, -2, -1, 0, 1, and 2 should work perfectly for your x values. So go ahead and use those, plot the points on your graph, verify it on your calculator to make sure you're getting the same graph. And because you can check these on your calculator, I'm actually not going to show you what these look like in the video. So pause the video, work through those 3 graphs, and then check them on your calculator to make sure they are correct. When you're ready to continue with the last part of the notes, go ahead and hit play on the video. Okay, so you should have graphed 3 equations, and you should have checked your answers on the calculator, so you should know at this point whether those are correct or not. So let's look at the last part of your notes. It says, many quadratic functions model real-world situations. We can use graphs of quadratic equations to analyze such situations. Typical things that involve quadratic equations are usually anything involving gravity. So I've seen quadratic equations used to model like a football that's been punted, as far as the shape that makes as it's kicked up, but then falls down because of gravity. The equations that come about from anything that's dropped from any sort of a height, or if you shoot a rocket up into the air, it will go up, and then after a while it comes back down. That also gives you a quadratic function. So there's lots of real-world things that are modeled very, very closely by quadratic equations. And we'll see just one example of that here. So example 2 says the distance d in feet that a skydiver falls can be found using the equation d equals 16t squared. Graph this equation and interpret your graph. How far would the skydiver fall in 4.5 seconds? And then part B asks what values of the domain and range are unreasonable. Explain. Okay, so just like we did with the other graphs, in order to graph this one, we are going to create a table of values. However, here, we don't want x, sorry, we want d and t. So we'll be putting in values of t for time, and we'll be getting out values of d for distance. Now here, it wouldn't make sense to use our typical values of -2, -1, 0, 1, and 2. This is going to start to answer question B. Think about, if I put in -2 for t, t represents time. What is -2 seconds? That doesn't make any sense at all. So here, we're only going to be able to use numbers that are positive. So good numbers to choose here would be 0, 1, 2, 3, and 4. Okay. And I didn't leave a column for us to actually work this out because this is pretty easy. Even for the larger numbers, we can put those in the calculator to figure out what we get. So when t is 0, you plug in 0 for t. 0 squared is 0, times 16 is also 0. When we put in 1 for t, 1 squared is 1, 16 times 1 is 16. Put in 2 for t, 2 squared is 4, 16 times 4 is 64. And put in 3 for t. 3 squared is 9. 9 times 16, if you use your calculator, it should tell you that is 144. And then when t is 4, we have 4 squared is 16, times 16 is 256. Okay. Now to put this on the graph, notice our numbers go up very, very quickly. So when we scale our graph, it might make sense to actually scale this so that each square is 25 instead of, obviously instead of 1, because that definitely won't fit. But that way we definitely will be able to fit all of our points on the graph. So we'll start at 0, and this will be 25, 50, 75, 100, 125, 150, 75, 200, and so on. 50, 300, 350. And when we label our graph, make sure we label the axes. This is distance, in feet. Okay. Along the x-axis, and this is where the time will go. And since we're only going up to 4 seconds, we don't want this to be 1, 2, 3, 4 and have the graph all squished in the space here. So instead we'll space these out a little more. So this will be 1, 2, 3, 4, 5, 6, 7. And this is time in seconds. Alright, so let's go ahead and put our points on the graph. Alright, we have a point at 0, 0. We have a point at 116. One at 264. 3, 144. And 4, 256. Okay. And you can see here that this is not quite a straight line. And if you looked at this, this has a squared on it, which means that that should be quadratic. So we should have a curved shape. Now, it doesn't have that typical U shape that you would be expecting because we don't have the other side of the graph. Because again, those negative values for time don't make sense. So this is just half of that U shape. So we'll go ahead and connect this with a nice easy curve. And it should look kind of like that. Okay. The question asks, how far will the skydiver fall in 4.5 seconds? Well, you can see, it also asks you to interpret the graph. You can see here that as time increases, the distance that the skydiver falls increases. But it increases a lot faster as time goes on. So he starts falling faster and faster as the time goes on. At 4.5 seconds, we can see on the graph that it's up here somewhere. We're going to want to use the equation to figure out exactly where. So at 4.5 seconds, we have d equals 16 times 4.5 squared. And we'll use the calculator to get the value there. So let's get out the graph. Okay, 16 times 4.5 squared. It goes out to 324. 324 feet. Okay, and to answer the last question, we've pretty much already answered this. What values of the domain and range are unreasonable? Well, it doesn't make sense for time or distance to be negative. So any negative values would be unreasonable. And why is that? Because time and distance can't be negative. Okay, so again, most of the focus for these three types of functions is just going to be on graphing. And try to, as much as possible, verify those in your calculator to make sure that you're getting the correct graphs. There are a couple applications with quadratics, but it's mainly, again, just graphing and interpreting what the graph looks like. So, or possibly like we did here, plugging in additional values for time or distance or whatever it is that's being modeled. But that is sections 9, 8, and 9, 9.